All right, and welcome everyone. We're live. Been a bit of a an adventure to get YouTube to talk to Vimeo, but managed to do it. So welcome to this weekly physics live stream. For those of you who just have stumbled in here by mistake or have never heard of this, my name is John. I was a GSI or teaching assistant, same thing, at Berkeley for many years and many years ago, and I was a GSI for Physics 8A and Physics 8B, which I enjoyed thoroughly. I have since then tutored physics at large, 8A, 8B, 7A, 7B, as well as a bunch of math classes for many years, and I found that to be quite enjoyable. And over the years, you know, talking to students and getting feedback and technology progressing the way it has, I got talked into doing a live stream. I tried it during COVID for a hot second there, and it worked out pretty good, but then I ran out of time and didn't have time to improve it and continue doing it. But we are now back, hopefully with a regular schedule, and with some improvements from last fall, where again we went through the whole 15 weeks and got a bunch of interesting feedback there. And so I live stream because I like to, and I teach physics because I like to, and hopefully it saves you time. Obviously, hopefully it improves your understanding of physics, but it saves you time in the sense that what has come out of live streams is that students go from lecture to discussion, and sometimes there's just a big jump there. Sometimes your teaching assistant might just be lecturing for himself or found some problems that he or she thought were cool, and they probably are, but they're just a little too far up there to get started, and they don't necessarily do the basics or talk through the basics at first. So my goal is to do this weekly and to basically recap the concepts of the week. Now we are like 2 weeks into the semester, so I'm a little late starting, but that was also feedback from last fall where students preferred to have this kind of recap a little bit later after having gone through lecture, discussion, and kind of dabbled with the homework a little bit, and then do a recap and say, okay, this is what you really need to know, and this is how to work through these problems now. So I started a little bit late just to make sure that you could get through all of kinematics, and I am going to catch up this week. So I'm going to do kinematics this week, both one-dimensional and projectile motion, and that should get us caught up and level set so that as you learn about Newton's laws next week, I'm also live streaming about Newton's laws, and then you can choose to watch this in whatever order you want. If you want to wait for lecture and discussion to watch this, you can. If you want to watch this before, you can. That's up to you. It's kind of the beauty of having it on YouTube and available at any time. So we're going to do the following. We are going to do these weekly recaps. The goal is to go over the things you truly need to know from lecture, and then practice on some problems. Usually I try to choose problems that they're either old exam problems or pretty close. I don't necessarily pick the hardest ones because again we're trying to kind of get our feet wet and walk before we run, but they're either inspired from old exams or they were at some point old exams or exams really, and so that's what we're going to be working on. As far as the homework goes, just a quick word. Depending on what homework software you use, I mean, Berkeley uses, we're not going to name what they use, but it's not the best choice in my opinion. If you want more resources to help you with that, you can go find them on my website. So you have here all the resources. If you want this live stream and you want to be able to go to a course that has everything packaged neatly in one place where all the weekly live streams are going to be, all the practice problems we're going to do will also be, and you have also a whole bunch of homework problems that are solved. You can go to Slackademia/live streams and sign up for the Physics 8A live stream. It's free. Just create an account. You can get in for free, and all the resources are there. Just nice in a nice nicely packaged in a one-stop shop. And if you need more resources, we have study guides either for Physics 8A, 8B, or whatever physics class you need. We can make study guides custom made based on your syllabus. Feel free to reach out if you'd like one. If you don't see your study guide or you're the class you're taking at a given university on our website, just reach out and we can make one for you. And the study guides are a simple subscription. It's $40 per month. You can cancel anytime. And you get access to lecture notes with videos, practice problems with solutions in video, and also solved old exams and practice exams. And if you want more help than that, you can sign up for the Masterclass. You can just choose Masterclass or study guide when you sign up. And the Masterclass is basically the same as a study guide, but you get access to me, and you can ask me as many questions as you want throughout the semester. And if you don't get some kind of A minus, or A plus, you get a 90% refund on the cost of your Masterclass. So you can't beat that. If you find a cheaper tutor, you should hire him or her, because that's the best deal in town as far as I know. But it is a good way to get as much help as you need in a conjunction between the website and also having a human that you can ask questions to if you're stuck or if you need help, like how to study, what to study, or confused about a topic or a problem. It is a good resource. At least many students seem to think so from previous semesters. So, with these shameless plugs and this administrivia out of the way, let's dive into today's topic, which is 1D kinematics. And it's interesting because 1D kinematics is probably one of the chapters that students hate the most. Now, I have a funny feeling that the reason why they hate it the most is because it's the first chapter that you learn when you take physics. And so if you've never taken physics and you get thrown into it and you start with kinematics, it can be a lot. And part of the reason that it's a lot is not because it's new, or not only because it's new. It's a new way of thinking, a new way of looking at the world. It's also because we perhaps don't talk about the math background of kinematics that much. We kind of just throw equations at you and assume that you're just going to learn them and you'll be okay, which eventually you are. But there's not really an explanation as to why kinematics have equations that look the way they do. So I'm going to try to clear the air and talk about that a little bit at first, and then we'll go over which kinematic equations you need to know and why. So let's start with parametric equations, or parametric curves. You can call it however you want. But this, if you have not learned about parametric curves in high school, this is going to sound brand new. If you have, well, it's a good time to kind of brush up and refresh. You're not going to need it that much. It's not going to get crazy. But it's just good to know that this is the lens through which we approach kinematics. Now, there's a reason for that. The reason is the following. So let's say you have a function, right? Let's say this is y is equal to f of x. Now we know that for a given function, one input x corresponds to one output y. So if your input here is x, let's call it x1 just to give it a name, there is only one output. It's not negotiable, right? It's the definition, in fact. F is a mapping, or a machine, if you want to think of it as a machine, to which you feed an input x and you get one single output y. And so if you feed x1, you get y1 based on what f is. F will tell you what to do with x to compute y. Fair enough. Now, because one value of x corresponds to only one value of y, you get what's called the vertical line test. So if you're given a curve, the vertical line test says, well, the curve is going to represent a function if and only if you move this vertical line, you will never intersect the curve more than once. All right? So here, obviously, if we do that, you can slide this thing around. You only ever intersect the curve once. All right? So vertical line test you pass it, it's passed. Like it's satisfied everywhere. Whatever this thing I graphed is the graph of a function. Now what function? I don't know, but the point is I can write it in the form y is equal to f of x, okay? And perhaps this is going to describe, I don't know, the path of a little RC car. You get an RC car, you know, for Christmas, and you go play with it on the street, and it, you know, goes around, and maybe it follows this path here, and in which case I can describe its path with a function y is function of x, right? Because it stays on the ground, it's flat, you know, you live in Davis or something like that, super flat. It doesn't, you know, you don't run it off a ramp, it doesn't fly up, it doesn't tilt over, it just stays in the 2D plane, so x, y in terms of x, good to go. Okay, now that's nice, but if you cannot fail the vertical line test, then you limit what paths you can follow with the car, which kind of sucks. That's not the point. In fact, it's the other way around. It's because the path that you follow with the car could be far more complicated than what I just drew. Probably y equals f of x is not the way to go. Okay, let's just take a very simple example. All right, let's say that this is going to be so this is xy, same thing. Okay, so there's the road. And now you're going to take the RC car, but you want to go around like this. Right? You want to make a figure 8. Keep going, right? You're pretty good at driving it. You want to make a figure 8. Okay, well this obviously is going to fail the vertical line test, right? There's no way that it satisfies. So this fails the vertical line test. Okay, which means that this cannot be written in the form of an explicit function y is equal to f of x. Okay, you can think of it in terms of values of x or values of y. If this is x1, you potentially have two outputs, y1 and y2. Well, which one is it? How do you know? Well, you don't know. It doesn't work that way. You can't write y is equal to f of x, have a machine, a function that takes one input and has one given output, and then say, oh, well, actually, JK, this time there's two outputs. So you cannot describe your car going around in a figure 8 with y is equal to f of x, which is kind of a bummer because most of the math that we've done so far when we come out of high school is y equals f of x. A lot of it, especially if you've taken calculus or even AP Calc, then definitely you're familiar with that. Now, if you took AP Calc BC, you're also going to be familiar with parametric equations, but point is, there has to be a way to describe the fact that the car is making this figure 8, right? Mathematically, I have to be able to describe this, right? Hopefully, anyway. I just can't do it with y is equal to f of x. All right. So instead, we introduce what's called a parameter, t. Usually stands for time. And what we're going to do is, instead of having y is equal to f of x, in other words, a direct relationship between y and x, we're going to do the following. We're going to try to express x and y in terms of t, this parameter, so that when the car is here, it's going to be at some x location and some y location, right? And if I tell you x and y, you know where it is. Let's call this x at time t1. This will be time t1. And let's call this y at time t1. Now t1 is your parameter. Again, you can think of it as time. But as t1 changes, x and y change independently from each other because each one is a function of t. So maybe you're going around like this, yeah? Okay, so a little bit later, you find yourself down here. Okay, so now you have, at time t2, a value x of t2. This will be t2. This will be x of t2. And y of t2. Okay, but the thing is, because x and y are a function of t, well, as time goes on, it's okay that you eventually do this, right? That you follow a shape that, yes, is going to fail the vertical line test, but it doesn't matter, right? Because we're not saying that this is what you have at any given moment. You don't have the entire curve, right? You just can draw the curve if you want to draw the memory of where the car has been and predict where the car will go. But the point is, you're not trying to write y equals f of x. So you're not violating any vertical line test here. You're just saying, okay, if I describe x of t and y of t, in terms of t, I get what are called parametric equations. Now, in some simple cases, you can take your parametric equations and do what's called eliminate the parameter, meaning you eliminate t between them, and you actually get y in terms of x. Sometimes it works, not all the time, but sometimes it does. We'll see that when we talk about projectile motion, where you actually can get rid of t and get y in terms of x. But in general, it doesn't have to, and that's the beauty, is that it doesn't have to. The path that I'm going to follow with my RC car could be anything. I can describe it in terms of x and y, both functions of t. Might be hard to find the right function, that depends, but if I can find a function for each one, then I can describe any path followed in the xy plane. And if I wanted to add a z coordinate, so an altitude, I could even describe any path in 3 dimensions. So, with that said, we are going to approach all of kinematics from this lens. We're not going to try to write y is equal to f of x. We're going to write x in terms of time and y in terms of time. In fact, at first, today, we're only going to do one or the other. We're either only going to write x or only going to write y, because we're just going to be moving in one direction. Right? So today I have a couple problems. One's free fall and one is launching a rocket, so it's going to be along the y direction, but only one direction at a time today. Okay? Next week, or next live stream rather, we'll do projectile motion. That'll be x and y at the same time, and we'll have both x a function of t and y a function of t. And in addition to x and y, we'll see that we can even go further. We can define the velocity of this particle at time t1. We can say that at time t1, it has a velocity, maybe we call it v of t1, and there's a way to get the x component and the y component of v from x and y. We'll talk about that further, but we'll just say that the x component is going to be vx of t1, the y component is going to be vy of t1, and again, I'm going to have vx and vy are parametric functions. They're functions of this parameter t, and at any given moment, if I plug t into v of t, I get the coordinates, or the components rather, I should say, the components of my velocity vector. So it's very useful notation. It's very compact. It's just a matter of knowing t, and then you can know vx, vy everywhere. You could do the same thing with acceleration. Now we're going to talk about that next, because we do make a simplifying assumption about acceleration in this class. But I figured I would spend, 10 minutes at the beginning just going over this to clarify why it is that we get equations x in terms of time and y in terms of time. I mean, intuitively it makes sense. Okay, yeah, x is going to change as time goes by. I kind of get that. But mathematically, the motivation comes from the desire to be able to represent the trajectory of any object that's moving without putting it in a form y is equal to f of x that restricts the shapes that I can draw. Right? Again, if it's y equals f of x, I can't fail the vertical line test, and then I can't draw a figure 8, for instance. So anyway, that's all for the math. I don't mean to nerd out on it. I just think it's a bit of, to level set everyone, to understand why, even though we've talked a lot in math about functions of the form y is equal to f of x in high school, we start off physics with kinematics with something that's not y is equal to f of x. In fact, it's x of t and y of t, which can seem off-putting at first. Okay, so with all of that, let's go ahead. Let me organize my tabs here. Let's go ahead and quickly review position velocity and acceleration. All right, so I am not trying to replace lecture here, right? So we're not going to go all the way and look at things from the point of view of lecture, where we define first the average velocity, and then we take the limit as delta t goes to 0 to get instantaneous velocity and all of that. All of that is fascinating and important, don't get me wrong, but that is not the goal of these reviews. These reviews are just to bring to the surface that which is the most important. And so kinematics, as a chapter, both for one-dimensional and two-dimensional motion, the goal is to explain how objects move, okay? Not why. Why is Newton's laws, whether it moves or it doesn't, to be determined based on forces acting on it. But how it moves is going to be kinematics. And in particular, I want to know where the object has been, where it is, and where it will be, how fast it was going, how fast it's going, and how fast it will be going, and what happens to its acceleration along the way. And we're going to make a simplifying assumption when it comes to acceleration because we want to keep things manageable without overcomplicating it with math. But the point is, we are going to talk about the relationship between position, instantaneous velocity, and instantaneous acceleration. Now, let's just assume we have something moving along the x-axis. To the left or to the right, it doesn't matter. It can change over time. But the position of the object that I have is given by x of t. Right? It's a parametric function or equation, function of time, and x changes with time. And if you tell me time t equals 7 seconds, well, I can compute x and I can tell you where this thing is. Right? If you say, well, where is it at t equals 10 seconds? I'll plug in 10 seconds and I'll tell you where it is. Right? So the position is given by, let's call it x of t. Now, position is one thing. Velocity is another. Okay, you can be somewhere, but maybe you're not moving, maybe you're moving to the right, maybe you're moving to the left. Velocity is going to be how fast your position changes. So v sub x of t is velocity, and it is how fast your position changes. Now, we can just keep that in mind for now. If you're comfortable with calculus, you'll know that that means that it's the derivative of position, d dt. If you take the derivative with respect to time, you're asking, well, how does x change with time, right? How fast does it change? And that's going to be your velocity in the x direction. And then velocity is in and of itself a thing. Yeah, you could be moving to the right. Maybe you have positive velocity then. Moving to the left, negative velocity. But your velocity could increase or could decrease or it could stay the same. Who knows? Or it could just change in direction, but maybe not in magnitude. So maybe you're going at constant speed, but in a circle. So that's what's called acceleration. Acceleration is going to be how fast velocity changes, right? So that's why we say that if you're at a stop sign or a red light, then you accelerate your car to get going. Well, accelerating meaning that you cause something called acceleration that changes your velocity. Your velocity goes from 0, you weren't going anywhere, to now, 10 miles per hour, 20 miles per hour, 25, and so on and so forth as you speed up, right? And so typically when we say we accelerate, we mean in such a way that velocity increases in magnitude, so the speed goes up, and usually slowing down is associated with deceleration, though we don't use that word that often in everyday language, but that's what it would mean if you were to encounter that word. So we have acceleration here, which is how fast velocity changes. And so it's the derivative with respect to t of v of x of t. Now, I wrote ax of t because in general, in the real world, acceleration might very well depend on time. It might change. Could increase, could decrease, could increase for a while, then stay constant. Who knows? The point is, though, that even though that's true, it becomes very complicated if you say, well, acceleration could be anything, so deal with it, and then your velocity could be anything too, but it's probably going to be more complicated. And then position could be anything too, in terms of a function of time, but then it's probably even more complicated. So Yes, in the real world, acceleration can change. However, in intro physics, we typically say, you know what, we're just going to study motion with constant acceleration. Good enough for now. Not to say that we won't ever look at acceleration that changes with time. Eventually we will. But at first, just to kind of get used to how these quantities are related to each other, we're going to say, you know what, we're just going to take acceleration as constant. Now, humor me, I'm just going to call it a sub x. But let's agree that this is meant to denote a constant acceleration. Okay, so we purposely simplify our analysis by only considering situations where acceleration is constant. And again, if it starts to change at some point, we can account for that. Once we're really comfortable with all of this, it's easy to make the problems harder. But at first, let's keep it easy. If your acceleration is constant, and if you agree with my derivatives here on the left-hand side, well, if taking derivatives takes you down from position to velocity and then to acceleration, then it follows that from acceleration, if you wanted to get velocity, you'd have to integrate acceleration with respect to time. And if you do that, and if a sub x is a constant, you get ax t plus some constant of integration c1. We know that from math. Now c1 is a great name for math. It's constant number 1. You know, everybody understands what that means. And in physics, we like to label things in a way so that when we see them, we know what they are. We know what they represent. Like if I see C1, be like, okay, constant 1, but is it a speed? Is it a temperature? Is it a, I don't know, a specific heat? What is it? So C1, not a great name, so we're not going to call it C1. It's going to be a constant, but it turns out that it's going to be v naught x. That is the initial velocity along x. Actually, that tracks. When t is equal to 0, this goes away. Here you should have the initial velocity along x, so let's call our constant v naught x. That seems fair. And so that's going to be velocity. If your acceleration is constant, your velocity is a linear function of t. If we integrate once more to go from velocity to position, then we're going to get 1/2 ax t squared, because t will integrate to t squared over 2, plus v naught x is a constant, so if you integrate it, you get v naught xt, plus some constant of integration, c2. Again, c2, great name for math, not a great name for physics. What am I looking at when I'm looking at c2? Well, if you think about it, when t is equal to 0, this goes away, this goes away. X at t equals 0 should be your initial position, where you are when the problem begins along the x-axis. And so instead of calling it c2, we are going to call it x0, the initial position. All right. So these are our kinematic equations, that under the assumption that acceleration is constant, we have x of t and vx of t that look like this. These are the standard forms of x of t and vx of t. Right? So you should be able to always write them in this form. You might want to make sure you have constant acceleration, but it'd be very surprising if you didn't. So in that case, you can just skip the math and the integration and whatever, and just write x of t is 1/2 axt squared plus v naught xt plus x0, and vx of t is axt plus v naught x. Okay, so that's how these things are related to each other, right? And so you'll see me say a lot that x of t and vx of t go together. Very often I'll start problems by writing x of t, and we'll write this. And when we write this, what we should keep in mind is, what are we trying to do with these equations? So, okay, I have a problem with constant acceleration, now what? Well, the goal when it comes to kinematic equations, and since these two go together, I usually put a curly brace or something to show that they're kind of related in a way. But the goal is to find these three things. If you find acceleration, v naught x and x naught, then you're good to go. Because then you know your kinematic equation. In fact, you'll also know Vx of t, for that matter. Now, Ax, for now, acceleration, for this chapter, because we have not learned about laws yet, we're just going to be given acceleration. Right? The most complicated case will be, it's not directly given, but, oh, we have free fall, so, okay, so then it's acceleration due to gravity. Downward, so usually negative, but, okay, I don't have to compute it. You're telling me. So for the first chapter, someone tells me either I'm in free fall or that the acceleration is, I don't know, 7 meters per second squared or something, and then fine. Okay, but I don't have to do anything special to find acceleration. That'll come when we learn about Newton's laws. Then v naught x is the initial velocity. That's typically given by the problem. You know, because the problem tells you, whether you're at rest or not at first. And then x naught is your initial position. That's usually up to you, because you can choose where to put the origin of your coordinate system. If the problem does that for you, then, well, you go with it and you just, use whatever definition they used or they chose for the origin. But otherwise, you get to pick the origin of your coordinate system and therefore x naught. But the point is, that's what we're trying to find every time. And then, in addition to these two equations that, again, sort of go together, there's this lonely equation that is its own thing, and it's not really a function, right? It's not a function of t. It is a relationship between quantities that, in fact, does not involve time, which can be very useful at times. That's going to be v final along x squared is v initial along x squared plus 2 a sub x delta x. All right. And I said delta x and I wrote delta t, so congratulations. There we go. Delta x. I just said it's independent of t. All right, so this is a relationship between quantities. Now, it is independent of time. In fact, it comes from, you put these two in a salad bowl, you shake enough, this thing will come out. You'll eliminate time between them, and you'll get that equation. And sometimes that's nice. If you say, well, how fast is the car going after 100 meters? Well, it's just, what matters is the 100 meters, not how long it took to cover the 100 meters. You could figure that out. You could say, well, how long did it take? And then now I know time, so I'll plug it into here to figure out how fast it's going, which is fine. Or you can just use this. Your displacement delta x will be 100, and then you can find v final x squared, because you probably know this and this. So anyway, these kinematic equations, I leave them like this, and I would argue those are the three you need to know. Are there other kinematic equations? Sure, there are. And, it's completely fine to use them if you want. You can do the average of speeds times time is delta x or whatever. That's fine. I don't have a problem with it. My point here is that if you can answer any kinematics question with these three equations. So I'm not saying don't learn the other ones. I'm saying focus on these, because you should probably be able to get the job done just with these. And now and again, if there's another equation that was introduced in class, sometimes that equation's faster, true, but it is still the case that you can always answer everything with these equations here. Meaning that in a given problem, these are the equations we want to use, and therefore we want to figure out acceleration, initial velocity, and initial position when faced with a kinematics problem. So, with that said, let's agree that if you are creating a cheat sheet, which I actually encourage you to do, if you find it helpful, you should do it. I would create a cheat sheet for each chapter. So as I learn, I would write down all the formulas that I learned in lecture. Maybe one formula shows up in a problem and maybe I missed it in lecture, or maybe it wasn't taught, or maybe it's just a useful formula in general. Could add that to my cheat sheet. Maybe I also add examples and problems to my cheat sheet that were helpful, so that by the end of the chapter I have, a little notepad or, a little notebook or whatever it is of formulas, examples, and problems about kinematics that are the most important things that I came across while I studied. And that's kind of my go-to now. I can go to there and look at that and try to solve problems. I can maybe add to it over time. And it's just kind of a nice tool that you typically don't get to bring into the exam room with you, but it doesn't matter. The point is to kind of collect the important things as you go, including examples that you found compelling or made sense to you, or even problems, so that you're like, well, this problem made sense. I want to make sure that I review it and I remember it, because, well, probably is going to be the case that if it made sense to me, something similar, if it's on the exam, well, it'd be helpful to refer to this problem. So you don't have to do this. I'm not saying everybody likes it, but over the years I've found that a lot of students find it helpful. Just kind of, it sifts through stuff. It's kind of a way to keep yourself accountable week by week as you go. And it's a nice tool to have before exams. So in particular, if you put examples and problems on your little cheat sheet or whatever you want to call it, which doesn't have to just be one page. Like, don't focus on that. Just stack papers with important stuff on them. But then you can go through those important examples and problems as you go and bring them back to the top of your mind. And you can actually probably go do that for each chapter that's on the midterm. Whereas, 2 days before, if you set out to do all of the practice problems that you've seen and done and not yet done, that's usually impossible. So anyway, it's a recommendation, but if you do it and you find that it's a waste of time and you're not learning anything, stop doing it, because your most precious resource is time anyway. Okay, so let's then move on to, real quick, talking about velocity and acceleration and how they're related to each other as far as motion goes. So this will be x, because this is the x-axis. And let's say that I have, it's a car driving down the road, right? And this car is going to the right. So then Vx of t will be positive. It might change with time, but as long as you're moving into positive x direction, your velocity is positive, okay? However, if the car starts backing up out of a parking spot, or maybe this is just the other lane of the freeway, and the car across the way is going the other way to the left, well then, velocity is going to be negative, okay? So the sign of velocity tells you something about the direction of motion. And let me just, actually I'll do this. No, not that. Hold on. There we go. Let me duplicate this. So that, because I'm going to have 4 scenarios total. Okay. All right, so then moving to the right, positive velocity. Moving to the left, negative velocity, because we said to the right is positive, right? If you want to change x and make it positive to the left, you get to do that. Then positive velocity is to the left and negative velocity is to the right. But the plus or minus is useful because just by knowing if the velocity is positive or negative, you actually know not only how fast you're going, that's the absolute value, but you know in which direction. Okay. Now then we have a couple of other options, actually 4 different scenarios. You could have an acceleration that also points to the right. So I'll just call it AX because we said acceleration is going to be constant, okay? And AX, what it represents, let's just give it a value, okay? Let's call it 1 meter per second squared. Well, what it represents is the amount by which velocity changes every second. So here, velocity changes by 1 meter per second every second, 1 meter per second squared. Which means that because acceleration points in the same direction as velocity, well, in magnitude, velocity is going to increase. All right. So in this scenario here, speed increases. So if your acceleration is in the same direction as your velocity, your speed increases. However, let's say that we maintain an acceleration to the right while velocity to the, an acceleration to the right while the velocity is to the left. Well then, every second you're adding 1 meter per second to the right, which is going to subtract from this. It's going to make it smaller, smaller, and smaller. In fact, until you reach 0. If you keep going, then velocity is going to start growing in this direction, okay? But the point is, up until the moment when you stop, your speed will be decreasing here because acceleration points opposite the direction of velocity. All right? Okay, so it's going to be the same thing here, right? It's just the same scenario but flipped. So here, because acceleration points opposite the direction of velocity, your speed will be decreasing. Right? So that's the case when you're slowing down, right? Like your velocity, you've been driving fast on the freeway, your velocity is forward, but, well, you hit the brakes because you need to slow down because you're, I don't know, there's an exit or something coming up and you want to take it. Well, then by hitting the brakes, you actually create an acceleration, a negative acceleration that decreases your velocity, right? But it doesn't mean because acceleration is to the left that you immediately start moving to the left. No, it means you start shaving off velocity to the right up into the point perhaps where velocity becomes 0, or it doesn't have to. Maybe you just drop velocity to 30 miles per hour and that's good enough to take the exit. So, by the way, don't slow down before you've taken the exit typically, because that's, but this is not a driving lesson. This is just physics. But the point is, velocity can be going forward and you can have acceleration in the other direction. It just means you're slowing down. Whereas if acceleration is in the same direction, you'll be slowing up, speeding up. And so here, of course, if we maintain an acceleration to the left to illustrate this, well, this time we're going to be speeding up to the left. The speed will increase. By what amount? Well, by 1 meter per second every second. That's what it means to have an acceleration of 1 meter per second squared. So, with all of that said, let's kind of dive into some practice and see, on a practical level, how one might take these kinematic equations, set them up for a given problem, which is usually the hardest part, and then use them to answer any questions that are given. But if you can get your kinematic equations, well, typically you can answer any question that revolves around kinematics. So we're going to do that. And by the way, I do encourage you to spend as much time as possible on kinematics. First of all, because the first 2 live streams are going to be kinematics. There's a lot of kinematics just off the bat, but kinematics have a tendency to find their way into the later chapters as well. Okay, so when we do Newton's laws, yes, we will focus mostly on Newton's laws, but we still need to remember kinematics. And you could mix a problem with Newton's second law and kinematics. Probably be an interesting problem. So you can't just forget about kinematics after the first 2 weeks. You have to be able to, recall kinematics and set them up again. You'll see that even when we do fluids, we'll find that fluids follow kinematic equations when they flow through the air, right? If you're not convinced, you can go look at a drinking fountain and the parabolic shape that you get. That is the same thing as projectile motion. So kinematics are very important. They're worth spending time on. All right, let's come down here. Now we're going to start, again, my goal is to, start with maybe something that's on the easier side, but that's going to teach us a few fundamental skills that we're going to need in order to set up more complicated problems. So we're going to do this free fall, vertical free fall, of some ball falling from rest and that bounces off the ground. And then we're going to look at a rocket being launched up into the air. And we'll see that, we'll talk about why the rocket problem is harder, what are the reasons for that. But we'll see that the same logic that we have here is just something that we reproduce in that problem. In fact, perhaps we reproduce it twice, but It's always the same thing that we're doing, right? So a ball falls from rest from a height h of 100 meters and bounces off the ground. Fair enough. So h is 100 meters. Y is positive up. That's the problem chose that, so I have to, roll with it. Y is equal to 0 at ground level. Also a choice that the problem made, but I mean, it's a pretty common choice. We typically measure heights from the ground up, right? So it makes sense. And we want to figure out how long does it take the ball to hit the ground, and then what is the ball's velocity when it hits the ground. Okay. Now, how long questions that involve time, usually, not exclusively, but usually have kinematics written all over them, because the only equations that we have that are directly a function of time in physics are kinematic equations, at least in intro physics. Now, there's a few exceptions, of course, and in general that's not true, but okay, if you're taking intro physics and you've never taken physics before and you have to solve for time, more likely than not, you're dealing with kinematics. So how long does it take the ball to hit the ground? Well, I don't know, but I can say a few things about this ball. First of all, it falls from rest, which means that its initial velocity in the y direction, let's call it v naught y, is equal to 0. Second, it's released from 100 meters above the ground. So I'm going to say that y0, the initial y position of the ball, is equal to h, which is 100 meters. Okay, y is 0 at ground level, so since the ball starts 100 meters above the ground, then y0 is h. Then the question is, well, what is my acceleration? Now this goes back to what I said earlier, when I said, at first we don't have tools to find acceleration. We need Newton's second law to do that, and we don't know what that is yet. So the best that we can do for now is either directly be told what acceleration is. Maybe a problem comes out and says, well, acceleration is 8 meters per second squared. Go have fun with that. Or it says, well, we're dropping a ball, or we're throwing a ball downward, or one way or the other, you end up with something that's free falling, which means that it's falling under its own weight, which is not a great definition because we don't know what weight is, but in common words of everyday life, you understand what that means. It's that you just drop something, or you could even throw it downward if you want, but it will fall under its own weight. There's nothing else. We neglect air resistance. The thing doesn't have a parachute. It also doesn't have a little rocket engine that could speed it up toward the ground or upward. None of that, right? So that is free fall. And if you are undergoing free fall, by definition, you will have an acceleration equal to g. G is the acceleration that exists everywhere around the surface of the Earth. It's 9.8 near the surface of the Earth. If you get further away, it drops, but as long as you're reasonably close to the surface, it's 9.8 meters per second squared. And it is just an acceleration that you possess by virtue of being near or on the surface of the Earth. Now, we don't feel it directly because we're standing, so it pulls us downward, but we're not falling because the ground stops us. But if we were to jump off, a diving board, that acceleration would accelerate us downward, right? So as we went up, it would slow us down because we move up and gravity is down. And then we stop and we start moving down with gravity. So we speed up as we go down. And it's just there because of how massive the Earth is. That's how it is. Which means that the acceleration AY of the rock, from the moment that it's released, and it's no longer in contact with my hand, is going to be the acceleration due to gravity, g, 9.8 meters per second squared. However, g points down, and down is negative. Down is negative because of this. So minus g is going to be the proper acceleration. All right. So how long does it take the ball to hit the ground? I don't know, but I'm going to start with my kinematic equations. So I'm going to write y of t is 1/2 ay t squared plus v naught yt plus y naught.
and then Vy of t is equal to Ayt plus V naught y.
All right, and as I said before, the first thing you want to do in any problem involving kinematics is find these three things. If you find acceleration, initial velocity, and initial position, you're good to go. It turns out we have all three, okay? And again, this was given by the problem. This was also given by the problem, it turns out. And this we just had to know, okay? So we are going to have y of t is going to be minus 1/2 of gt squared plus, well, 0 because there's no initial velocity, plus h then. And then this is going to be minus gt. And these equations will describe the position and the velocity of the ball as it falls. However, once it hits the ground and bounces back up, well, these equations are no longer valid. What I would have to do is I would have to say, well, now bouncing back up is kind of like, in and of itself, it's a problem. It's a different problem than what we just studied. So maybe I set up new kinematic equations for that. That's an option, right? We'll see how to deal with multiple phases of motion in the next problem. But here there's only one phase of motion. You drop the ball from rest and it falls and it hits the ground and the problem stops. We just don't care what happens after that. We just want to know the velocity when the ball hits the ground, okay? So we have done, in a sense, the hardest part because we've said, okay, here's the ball. Let me make a copy of this. No, come on. There we go. All right, put that here, okay? Here's the ball. This is t equals 0. And it's going to fall down like this. And it's a certain time, I don't know, call it t final, just to give it a name. It is going to be moving downward and is going to crash into the ground. All right, so this is going to be Vy or V final, whatever you want to call it. Let's call it V final. Okay. Well, V final Y is probably a great name, so let's call it V final Y. All right. And of course, V final Y is down and up is positive, so my anticipation is that velocity should be negative when it hits the ground, but we'll see. Okay, so then how do I go from my equations to finding velocity? Well, here's the thing about physics. Here's why, if you've never taken physics before, hopefully you like it still, but if you don't like it, one of the reasons might be because it's very different than math. Math, the problem is set up for you, right? In calculus, you're given f of x. F of x is, I don't know, square root of x squared plus 1, whatever. It is what it is. And then you can go around and play with it. You can compute a derivative, a double derivative, find the equation of the tangent. God knows what you can do. But f of x was provided off the bat. Well, in physics, typically the problem is not set up for you. You have to set it up. In other words, nobody gave me these equations. I had to put them together. And that's kind of the hardest part at first, is to get used to reading a problem, putting it into equation. Reading a problem, put it into equations. Once you have these equations, they describe the position and the velocity of the ball throughout its entire fall. So I do not need other equations than this. I just need to know how to use them now. Okay, so how to use them? Well, we have to write things that are true. Now, everybody laughs when I say that because, well, duh, do you want to write things that are wrong? It's not what I mean, but I get it. When I say you want to write things that are true, it means that it is very difficult to think of physics, especially if you've never taken physics before, in the following way. I'm at A, I want to get to C, and I can already foresee in my mind that I'm going to have to go from A to B and B to C. I'm going to do all these steps and it's going to work. I'm not saying you can't get there. You can. It just takes a lot of practice, and it's not necessarily a good goal for this class, right? If you can get to that point, I mean, fabulous. Good for you. And you'll be better off for it. But it is very hard to look at a problem and know exactly in which direction to go in physics, especially when we start to mix concepts together. And so the better way to think about it is that you want to write things that are true, in other words, things that are relevant, and that have to be true based on the information that you have. So for example, the problem wants me to find how long it takes to hit the ground. So it wants me to find t final. First of all, I'll give it a name. But second of all, what has to be true at t equals t final? In other words, what must be true when the ball hits the ground? Okay, so at t is equal to t final, what has to be true? Okay, now we should be able to make at least one statement based on these equations. But I have two things going on. First of all, the velocity upon impact is not zero. Okay, like this is true in general, and you need to remember this. If you're asked to find how fast is the cannonball going when it crashes into the cannon wall, or how fast is the ball going to strike the ground, the answer is not zero, right? Your velocity will be zero, yes, after it crashes into the ground, but at the moment of impact, your velocity is not zero, okay? It's really simple. If you are a manufacturer of cannonballs and your goal is to make cannonballs to destroy the fortress in the Middle Ages, and you sell cannonballs that have zero velocity upon impact, you will go broke. And in fact, they will probably come find you because those are the shittiest cannonballs that you can make. Right? That's not the point. The point of cannonballs is to have a lot of velocity and mass for that matter, but upon impact, so that you destroy the castle wall. All right, so upon impact, if something is going to crash into something else, the velocity is not zero upon impact. Yes, it's zero after, true. Let's say the cannonball embeds itself in the castle wall without breaking it. Is the velocity zero then? Yes, but that is not upon striking, that is after striking. That is after the wall sustained damage to slow it down with a deceleration to a stop. So, just something to keep in mind. So, let's not start by saying that velocity is zero. It isn't. In fact, if we call it VFY, what it's going to be, based on this, is it's going to be Vy at time t final. That's by definition what this thing tells me. This function tells me velocity at any time. Well, if I knew what t final is, then I could say, well, it's Vy of t final, right? So that has to be true. The other thing that has to be true is that when you hit the ground, albeit with non-zero speed, well, you're back at your reference for y as defined by the problem. And so it has to be true that y at time t final is zero. So we have to have y of t final is equal to zero. And we can also say, let's call it v final y is equal to Vy of t final. Okay? And again, this, along with setting up your equations, is the hardest part of physics. And if you do physics and you try to solve problems, you should, by the way, only ever solve problems that have the answer somewhere to them. Don't solve problems without answers. You're never going to learn anything. Preferably detailed answers. If you skip through that part, and you're like, yeah, okay, I get it, and then you just start solving from here on out, you're missing the most important part. This is what's going to play tricks on you on the exam. Because solving the math that comes from this, I mean, anybody can do that. Like, you'll see. What is the math that comes from this? Okay, well, let's write it out. What is y at time t final? Okay, well, y of t is this. So at time t final, the best that I can say is that it's minus 1/2 of g t final squared plus h, and I want that to be 0. And then I'm saying that v final y, which is what I'm solving for, is going to be Vy of t final, that's minus g times t final. Okay, so if you give me t final, I'll find this, which is what I want. How am I going to get t final? With this, right? So quick sanity check. 2 equations for 2 unknowns. Therefore, we're good to go. We can solve. And in fact, solving the first one is the easiest thing to do. You'll get t final. And that's, first of all, how long it takes. So that's what we want to know. Then we want to know the velocity of the ball when it hits the ground. That'll be v final y. So we first solve
equation 1, which is going to be minus 1/2 of g t final squared plus h is equal to 0. That's going to be 1/2 of g t final squared is equal to h. All right, t final is going to be plus or minus, careful, square root of 2h over g. Okay, but negative time makes no sense. So we only keep the positive root. And we say that t final is going to be square root of 2h over g. Okay, now it's going to be square root of 2 times 100 divided by 9.8, and that's about 4.5 seconds.
Okay, and so that's t final. Now, I do want to emphasize this part here, the plus or minus part. You will see in physics, because a lot of times we solve for something that is implicitly positive, like time or speed, we kind of get a little loosey-goosey and we jump from here to here, right? Which we shouldn't do, because, you know, if you're going to toss one of the roots, you should be convinced that you're allowed to do so. Okay, but it's so common that even I do it, and I shouldn't. I know I shouldn't, but I still do it. And we go from here to here and like, oh, t final is this. Okay. Most of the time it's not going to be an issue, but you should still always ask yourself, if you're going to throw out a root, is it going to be an issue later? Because sometimes you need both roots. Sometimes you need to keep the negative one. So something to keep in mind. But here we have t final is going to be 4.51 seconds. We keep the positive root because negative time doesn't make sense. At t equals 0, the problem begins, and time only moves forward from then on out. Okay, so then what's the ball's velocity when it hits the ground? Well, I just found how long it takes to hit the ground, yeah? Now, something to keep in mind with kinematics, once you know time at a given point, here when you hit the ground, you know everything, right? You know position, you know velocity, you can solve for anything because everything's a function of time, all right? So yes, I solved this to get t final, but now that I know t final, all I have to do is plug it into this to get v final y, all right? And so v final y is going to be minus g t final. That's going to be minus 9.8 times 4.51, which is approximately equal to minus 44.3 meters per second. Yeah? All right. Now, by the way, negative makes sense. When the ball strikes the ground, it is moving downward. And up is positive, so down is negative. Therefore, negative velocity tells me I'm moving downward. All right. Now, with that said, I found first time and then velocity upon hitting the ground. I want to redo the question about the velocity upon hitting the ground using a different method, which is not the fastest way to do it if you've already found time, right? If you already know t final, the fastest way to do it is just to plug in t final into vy of t. But let's say that you didn't find t final. Let's say that you have duplicate all this, okay? And that you're just asked to find this velocity. So this is an alternate method. Right. And it's the goal is to find this guy. Okay, well, okay, so if we're going to find this guy, we don't really care about time. Right? If the problem just says, well, how fast is it moving when it hits the ground? What's the velocity? It's like, well, I could find time. If I do find time, then I know how to get v final y. We just did that. But if you just want me to find v final y, probably I'm not going to use time.
Probably I'm going to do the following, just as a reminder so that we have everything. AY here is negative g, right? Well, we're going to use v final y squared is equal to v naught y squared plus 2 ay delta y. Now this is 0, so this is going to be 2 times minus g, and the change in y is y final minus y initial. Well, that's going to be 0, y final, minus y initial is h. Okay, so we are going to get v final y squared is equal to 2gh. All right, so v final y is going to be square root of 2gh,
Be careful, plus or minus. Okay, really important. Plus or minus because, hey, could be one or the other mathematically. And in fact, in this case, I need to choose the negative root because my velocity's got to be negative if I'm moving down.
all right? So here we keep the negative root because v final y needs to be negative if it's going to describe me moving downward. So v final y is going to be minus the square root of 2gh, which is going to be minus the square root of 2 times 9.8 times 100. That's going to be equal to minus 44.3 meters per second. Okay. By the way, I strongly, strongly, strongly encourage you to become comfortable with variables only as quickly as possible. And you can fight it, you can kick and scream and yell to the wind. It won't change the fact that the sooner you accept it and you just yield, the better off you're going to be, right? Most problems, in fact, on exams no longer have numerical values. It kind of depends who's teaching, that's true, but a lot of times they don't. And you're asked to do everything with variables, which is what we're going to do in the next problem. But the sooner you get used to it, the better. Right? Plug in values at the end. There will be a time to plug in values, but get comfortable as quickly as possible manipulating just variables, because it is how it's how we have to teach you physics, because it's just how you should do physics. It makes a lot of sense to use variables. Because again, we tend to choose variables, first of all, that denote quantities that we can recognize. I mean, g is a constant, but I know it's an acceleration. H is a height, so it's meters, and so it conveys not only what it represents, but also the units of, what it represents. So it's very useful to have variables. And then, physics is an applied subject, right? So usually you don't just want one answer. Like maybe you are studying how fast the ball strikes the ground as a function of height, let's say. Okay, and so now let's say you redo an experiment where h is not 100, it's 200. Okay, well, fair enough. I'll just plug in 200 here instead of 100 and I'm done. There's the answer. Whereas if I have to re-derive everything because I plugged in 100 here and now I don't remember where the 100 came from or what happened to it in between, I got to redo the whole derivation. I don't have time for that. We all got stuff to do. So we use variables into the end like that. If you want to double the height on me, I can say, well, doubling the height will cause the speed or the velocity to go up by square root of 2 in absolute value, right? So that is my little me advocating for variables, but I'm not the only one. You'll see variables are the way you should go about physics, and then you plug in values at the end if you have values to plug in even. Okay, so that was a bit of a long problem. It was certainly longer than it needed to be, but it's the first problem that we do, and so we need to kind of get used to
setting things up. We need to talk through things, and the goal is for this to be a foundation so that you can go do other similar problems. Okay. Now this one was in fact a little bit on the easy side because, well, there was one object and one phase of motion, right? The object is the ball or the rock or whatever it is, and you drop it, it falls to the ground. One phase of motion because we only care about the fall. Maybe the ball bounces off the ground. That might be a second phase of motion. Just don't care about it, right? So one object, one phase of motion, okay? Let's see what happens now if you have one object but two phases of motion, okay? Now you could, and you could go from there. Yeah, you could have two objects and two phases of motion, or two objects and one phase of motion. Okay, so it's important to know what you have and how many kinematic equations you should write. But let's have a look at this rising rocket problem. Now this one is so classic it's not even funny. It's been on so many exams in one form or the other that it's definitely worth talking about. So a rocket rises vertically from rest, presumably from the ground, with an upward constant acceleration of AY until its fuel runs out at a height of h. After this point, the acceleration is that due to gravity alone. Okay, fair enough. Calculate the speed of the rocket at the instant it runs out of fuel. How long does it take to run out of fuel? And then find the maximum height that the rocket reaches. Okay, let's start by drawing this out. Okay, so I'm going to have the ground here. This obviously is going to be a rocket. Okay. And this rocket will be launched from rest. It is going to reach a certain height where it runs out of fuel. But when it runs out of fuel, is not, let me move this over here for later. When it runs out of fuel is not when it starts to fall back to the ground, yeah? Because when it runs out of fuel, it was being accelerated upward. It now has a certain speed, and it will keep going. Certainly gravity is going to slow it down to the point where it stops, and then it starts to fall back down. So the tricky part is first to realize that the total height reached by the rocket is not just the height h where it runs out of fuel. It's going to go higher than that, okay? So let's call this a certain height, which is actually little h. And then this is going to be another height, right? Okay, so we need to set this up, right? There's a few things we need to find. We need to find acceleration, initial velocity, initial position, and then try to figure out the speed of the rocket when it runs out of fuel. Okay, so we are going to make the ground y is equal to 0. In fact, I'm also going to choose y is positive upward. Okay, you can't see that, can you? Oh, there you go. There we go. All right, then this is going to be y1 is equal to h. That's the height when it runs out of fuel. At a time, I'm going to call it t1. This is t equals 0 on the ground. And then here we're going to get to y2 is equal to, I don't know, let's call it h2, right? Or actually, you know what? Let's call it big H, right? It's a bigger height than little h, so let's call it big H, fine. And that's going to happen at a time t2 potentially, but we're going to have to talk about t2, be a little bit careful about t2 later on. So right now I'm not going to write t2. I'm just going to say y1, y2, and at time t1 we run out of fuel. And on our way up from the ground to t1, we are going to have an acceleration that the problem says is ay. It has to be upward so that it accelerates me into motion, right? It has to increase my velocity upward so that I start moving upward. Okay, but then later on, once the rocket runs out of fuel, the acceleration is that of gravity alone. So now our acceleration ay is minus g. And again, minus because up is positive. Here it's just called AY. That's the name the problem gave it. Fair enough. Okay. So this is what I mean when I say that there are two phases of motion. Right? There's a first phase here where you're accelerating upward. You can set up kinematic equations for that. They will describe that part of the motion. But those equations cease to be true the moment you run out of fuel, because now you're going to switch from this acceleration to this acceleration. So everything changes. So this is a second phase of motion. The second phase of motion deserves its own kinematic equations. Okay. Now somehow it has to remember the first phase of motion, obviously, right? Everything's related. And the way it's going to remember is by saying that, well, here, if this is V1, right, which is going to be, by the way, Vy at time t1, well, this V1 is going to carry over. And for the second phase of motion, this V1 will act as an initial velocity for the rocket for that phase. Okay, so we're not going to try to get ahead of ourselves too much. We're going to do this in one question at a time. But if we're preparing the groundwork a little bit, what transfers over from one phase to the other is V1. But you have to treat the two phases separately. Okay, so let's find the speed of the rocket when it runs out of fuel, which is V1. Okay, now to do that, let's set up the kinematic equations of the rocket for the first phase of motion. Okay, so it's going to be y of t is equal to 1/2 ay t squared plus v naught yt plus y naught. Now, that's actually pretty nice. That's the standard form. And conveniently, the problem decided to call the acceleration ay, which is positive because it's upward. Okay, so this term is taken care of. I know my acceleration. And then v naught y is going to be 0 because I start at rest. And y naught is going to be 0 because I start on the ground. All right, and therefore, vy of t is going to be ay times t. Okay, now if we want to find the speed of the rocket when it runs out of fuel, we can do that, and there's two different ways to do it. All right, so there's option number 1. Okay, now I'm going to move this over and we'll come fetch this later when we need it, but for now let's just forget about it, right? So solution A, or solution number 1, is, okay, well, I will find the time it takes. Let's try to put this on one screen. There we go. I'll find the time it takes to run out of fuel, and then I'll solve for V1 because V1 is just Vy of T1. So if I know T1, it's easy to get. Okay, well, at time T1, what has to be true is that y of T1 is equal to this height h that I'm given. Right? There's only one time for which I reach that height. So y of T1 has to be h, which means that 1/2 of ay T1 squared has to be equal to h, which means that, okay, t should only be positive, so let's just keep the positive root. Square root of 2h over ay. And I can't do better than that because it's a variables only problem. So, like, okay, well, that's it. I can't go further than finding T1 in terms of h and ay. Okay? But now that I know T1, well, I can just say, well, Vy at time T1 is V1. So it's easy, yeah? I can just say this from here is going to give me V1 is Vy at time T1. Vy at time T1 is ay times T1, which is going to be ay times the square root of 2h over ay. All right, here comes the moment everybody hates. That square root of 2ayh, hopefully we all agree. But let's say we don't agree. Let's say you don't see where that comes from. Just as a quick reminder of square roots and exponents and all of that, this is basically a times square root of b over a. Right? If you absorb a under the root, you're going to get a squared b over a.
So that's going to be square root of AB. All right.
If you are shaky on square roots, on fractions, on exponents, and all of that, do not be too proud. Time to put the internet to good use, either a good old Google search for some worksheets on that stuff, or you know what, pop out Gemini, ChatGPT, whatever it is, and say, hey, I need a refresher on square roots, exponents, and fractions. Can you generate a worksheet of each with 10 questions in each worksheet and step-by-step solutions, and go for it, because that will be the best, I don't know, let's call it, say it takes you 30 minutes. The best 30 minutes you spend if you're shaky on that stuff, because you just can't go through physics without knowing how to divide two fractions or manipulate square roots and everything. It's just going to be painful for no good reason. And fair enough, these things are easy to forget if you never use them. If you haven't used them all winter break and you don't remember them, I don't blame you. I use them every day, so at this point it's fine, but I'm well aware of the fact that if you don't do it for a little bit of time, even a short amount of time, these rules, which are boring rules, are easy to forget. Okay, so that's solution A. Right? Solution A, very classic, by the way. You find time, even though nobody asks you to solve for time, but you needed it to find V1. So it's a means to an end. You're like, first step, I get time, and then I'll use that to get what you asked me to solve for. Like, that's fair. Very classic move in kinematics.
Solution B is the following.
Solution B is to acknowledge off the bat that, indeed, we do not care about time. Nobody asked me to find the time,
so I'm just going to use V final y squared is V initial y squared plus 2 ay delta y. And in so doing, I'm going to write V final y is going to be V1 squared is, this is 0, 2 ay is negative g. No, it's not. Sorry. Ay is ay. JK. Ay is ay. Acceleration is upward. Delta y is my change in height. It's h minus 0. Okay, so if I use that, come down here. All right. Solve for v1. I'm going to get v1 is square root of 2 ay h, which is exactly what we found above. Okay?
Up to you. You can pick whichever method you like, whichever one makes most sense. The fastest one is B, of course, because you don't have to solve for T1. But, well, the next question is, what's T1? So if you've already used solution A to find T1, you're like, well, we know what T1 is. It's square root of 2h over ay.
So question 2, right, you just say C above if you used method A for solving. T1 is square root of 2h over ay. All right.
So fair enough. Not bad at all, right? Typical kinematics questions, right? Okay. And then the last question is, well, calculate the maximum height that the rocket reaches. So this is where I need this guy here. Okay. All right. So from the moment that the rocket runs out of fuel, the problem changes because the acceleration changes. So whatever equations I had before, these equations are no longer valid. Okay, they no longer describe the motion of the rocket because they used to be valid for an upward acceleration ay. Now I have a downward acceleration minus g. So different. All right. So I need to set up new kinematic equations. Right. This is also something that a lot of students struggle with at first when you solve a problem, is that we don't have a lot of experience in problems where you have to set something up again from the get-go, you know, like from scratch rather, in the middle, right? Usually the problems that we've been solving in all of our classes have been like, find this, and you go find it and you're done. Okay, well here it's like, find this, this, and that, and then to find the last one, you actually have to start over and say, okay, what carries over from before, right? Well, I know what V1 is, right? V1 is the square root of 2
AY H. Okay, all right, we figured that out. And we know that the height is h. We also know the time t1 for that matter, right? So let's maybe just write everything we know. Okay, t1 is the square root of 2h over ay. Okay. Now I want to find capital H. Okay. Now to find capital H, let's think about this. Let's just write down what we know so that we can set up any kinematic equation we want. We have ay is negative g. We have v naught y for this phase of the motion is v1, which is the square root of 2 ay h. And then we have y0 is equal to little h, right? That's fair?
Okay, so now we can set up our kinematic equations just like we did before. We have the important pieces of information. Now if we take a minute and we think about this, we're not gonna, we could do solution A and solution B again, but come on. Why would we solve for time again when this is literally the same kind of problem, right?
Nobody asks me to solve for T2, right? Whatever that is. They just want me to solve for big H, right? So then what I'm going to say is that V2 here
is 0. That is what defines the max height. Max height has to be a turnaround point. The rocket is no longer moving upward. It is not yet falling. It just, that instant it is at rest. That defines the max height. And so V2 is 0. Okay, well, okay, then I can just relate V1 to V2 to the change in height through the acceleration, and I can be done. Now, certainly if you want to use kinematics and you want to use y of t is equal to minus 1/2 gt squared plus, let's just call it v1, and we can always plug this in later, but let's just call it v1 for simplicity, plus h is y of t. And then you can say, okay, well, vy of t is equal to negative gt plus v1. All of that's valid, and you're welcome to do that. But, okay, if you understand how we went about the first two questions of this problem, then hopefully we all agree that it is far easier to do the following, to say, okay, v final y squared is v naught y squared plus 2 ay delta y. Okay, well, v final y is v2 squared, which is 0, is equal to v1 squared plus 2 times negative g for ay, and delta y, now careful, that's going to be h, big H, minus little h. That's your change in height for that phase of the motion, right? All right, so this is going to give us v1 squared is going to be 2 ay h minus 2g h minus little h. Okay, so then, what am I doing? 2 is what I wanted to cross out. We're going to have 0 is equal to ay h minus g big H plus g little h, and we're solving for big H. So g big H is equal to ay little h plus g little h. And so if we divide by g, we're going to find that big H is equal to little h plus ay over g times little h. In other words, 1 plus ay over g times little h. Okay. Now, I know I tend to harp on this a little bit, but would I have ever guessed ahead of time that that's what the answer looks like? Probably not. At least I'll be honest, I would not have. Now, once I see the answer, I'm like, oh, it kind of makes sense. Yeah. I can see how there's a ratio of accelerations, and that probably makes sense now that I see it. But I never would have thought of it ahead of time, right? So what I had to do is I had to trust that if I write this properly, in other words, I write something that's true, that's this. From there, I either get a piece of information or all the information I need to get the answer. But I don't know how it's going to unfold. I don't know what it's going to look like. I kind of have to have blind faith that if I start with formulas that I set up properly, and I have enough formulas set up properly, out of them comes the answer. And that is a very different way of thinking about, but really it's just a different way of thinking, period, compared to all the other classes you tend to have taken. Right? It's just a different way of solving and a different way of approaching things. But the point is that what matters most is the relationship at first between these variables. And here there's only one because it's one-dimensional motion, so it's pretty easy. But in general, when we multiply problems, or when we multiply the concepts that are involved in problems, well, we will have multiple formulas that we need to set up. Maybe one for a collision, and then one for conservation of energy, and one for work kinetic energy theorem, and we'll set them all three up. We have no idea how they're going to play together in the end. We just do the first part carefully, and something comes out of it, which hopefully, if we do our math right, is the solution. But so again, I say that if you have, if you're hitting a wall, if you have like writer's block or whatever you want to call it, where you just don't know where to start and you can't see the path to the answer, yeah, it's actually hard to see the path to the answer. The path to the answer is take the formulas that you think are relevant, try to set them up properly, and then if you don't even know whether you have enough formulas to solve, count the formulas and count the unknowns. And they need to match, right? Because one formula, one equation in math allows you to solve for one unknown. So if you have 3 equations and 3 unknowns, you're like, okay, I can stop banging my head against the wall. I've written everything that I need to write to represent this problem. Now let's solve. And I don't know what the solution is going to look like. I'm not even going to try to guess, but I'm not going to mess up my math. I'm going to be careful, and what comes out comes out. Okay, and you can always check with units, right? This is a height should be in meters, h is in meters, and then 1 has no dimensions, no units, and a ratio of acceleration has no units as well. So we're really talking about meters equating meters. Turns out it doesn't mean we're right, but if we had meters equated to seconds, then we know for sure we're wrong. So units do help you at least kind of figure out if you've written something completely nonsensical or not. But here we're good, at least as far as units go. So this is actually going to be the end of this public portion of the weekly physics review. Hopefully this kind of made a bit more sense now that we've gone back and revisited kinematics after you learned about them. We're going to do the same thing, this week again. I'm going to live stream twice, which I don't usually do, but I'm going to live stream twice to catch up, to do kinematics today and projectile motion, which is basically more kinematics, later on Thursday. And like that, we'll be all caught up and we can, sync up with Newton's laws next week. But this is the end of the public portion of this physics review. If you want more resources, including these, you can go to slackademia.com. At the very least, the live stream course is free. It'll have all these live streams. It'll have the problems typed up so you can actually attempt them before watching the solution. And it has a lot of solved homework problems. So it's a good resource, and you can have it, for free if you're on a budget. It's a nice place to start. And if you need more help, well, there's more help obviously on the website. We can make a custom study guide for you if it's not already there. And if you want to sign up for a Masterclass so that you have access to me so I can help you all semester with physics, then you should consider it, especially since if you don't get some kind of A, our guarantee is that we will refund you 90% of the cost of the Masterclass, because I think that if I help you all semester, your odds of getting an A are pretty high. So anyway, with all of that said, thank you for watching, because if you don't watch, this doesn't work, and I appreciate your feedback and all that as always. Let's have some fun this semester, and let's try to get through physics together and make it as painless and efficient as possible. All right, have a good evening. Y'all take care.